So today's lecture, I kind of consider today's lecture to be all about finding the centers of certain things, okay? And so included in this would be centers of gravity. That is very closely related to centers of mass. This is also related to things like centers of volume and centers of area. And so we need to kind of define what we mean by that a little bit. But I'll just go ahead and tell you that these centers, to find the center of any one of those items I just listed, right? Gravity, mass, volume, or area, is very important in a lot of different aspects of engineering. And so we're going to look at how to do that and kind of what it means and that kind of thing, and a few applications of where we might need to kind of use this idea. So let me start with, I think the easiest one for us to understand is this idea of the center of gravity. And the way I always like to kind of start with this is to say, we intuitively typically know how to find the center of gravity of a body, right? So think of a body that's like a long, slender member like this one right here. What if I wanted to know where the center of gravity was of this? I could balance it on my finger, right? And if I don't get it here, why am I not getting it here? Because there's more weight to this side than to this side, and so if I let go of it, what's it want to do? Accelerate angularly that direction, right? So if I move my finger over a little bit, you know, eventually I can find that spot where maybe it's close to balancing, right? So we intuitively know how to do this and figure out where the center of gravity is of something. And that's actually a really good way to get started talking about what it even means to have a center of gravity. What I'm doing there is I'm basically trying a few different spots along the length of this thing, and what I'm looking for is the place where all of the moment reactions that would tend to try to rotate it one direction perfectly balance the moment reaction that would try to rotate it the other direction, and that's when it'll balance on my finger, okay? So let's think about what that would look like with respect to some discrete weights that might act along a line. So what you see on the screen there are several different weights, and they are all sitting on a beam that we'll just think of that beam as being weightless for right now. Imagine it's a very small amount of weight relative to the other weights that are there. How would I figure out that coordinate x sub c that I have labeled up there that would make it to where this thing wouldn't want to accelerate angularly one direction or the other around the fulcrum that I have there in the middle? What would we do? Okay, so I could figure out, I could basically figure out how much moment would each of these items create around each of those weights up there, how much moment would it create around the fulcrum. So what would that math look like? Okay. Yeah, so summing moments here about the fulcrum. Right, I'll take counterclockwise to be positive. How much of a moment would be created by W1? Okay. W1 times XC minus X1. Okay. What about W2? Okay. So plus W2 times what? XC minus X2. All right. Then what? Okay. We could say, and I'll go ahead and write it this way, minus W3 times what? X3 minus X sub C. But before I move on, would that actually be the same thing as saying, putting a plus here and reversing these two terms? That'd be the same thing, right? Mathematically speaking. So I'll just go ahead and do that because that keeps the same pattern of what I've been doing. And that really illustrates the idea that the next one is going to really be the same, right? It's W4 times X sub C minus, X sub 4. Okay? Those are all the moments that are created around that fulcrum point, right? And if I don't want it to accelerate angularly, what must the sum of all these moments be? 0. Okay? So, now here's a question for you. Could I expand each one of these terms out? In other words, if I expanded each one of these terms out, I would have like W1 x sub c, right? And I tell you what, just in the interest of making this clean, I could do that process for each term, right? So I could do W1 xc plus W2 xc plus W3 xc plus W4 xc. And then I could do all the other pieces too. I could say minus W1 x1 minus W2 x2 minus W3 x3 minus W4 x4. And this would be the same thing, right? All I did was I expanded out each one of those terms. Okay? Well, then what could I do? What could I do with these first terms over here? All right, they each have a common term, like a common factor in each one of those terms in that sum. And I could factor it out. I could say x sub c, right, times W1 plus W2 plus W3 plus W4. And this, the other thing I could do if I want is go ahead and move all my other terms, all those negative terms, I could move those to the other side of the equation. And I would say that this would be W1 x1 plus W2 x2 plus W3 x3 plus W4 x4. And you get the idea here. I did this with 4 masses. My pattern here, though, is it going to be held up if I go to more or fewer masses than 4? Like the pattern kind of stays the same. I could go to 5, I could go to 6, I could go to 3. Of these weights on this thing, and the pattern would be the same. The pattern being W1 plus W2 plus W3 plus W4 plus 5, 6, 7, right? All of the other terms that might also be in there. It's not going to get interrupted just because I take away of some of these weights or I add some more weights. Okay? All right. So what have I done here? I've basically set this up to where I can solve for x sub c. And x sub c just ends up being W1 x1 plus W2 x2 plus W3 x3 plus W4 x4 all over W1 plus W2 plus W3 plus W4, where the W's are all the weights of each of the terms. Okay? And like I was saying a second ago, the pattern doesn't care how many of these weights that you put on there. And because of that, is there a way I could generalize this pattern that I just put right there? So if I say generalizing here, what would I say? Okay, x sub c is just going to be equal to, we'll use this really slick summation notation, okay? The sum of an index that goes from 1 up to however many pieces I have, and in this case I would go like from 1 to 4, right, of w sub I, x sub I, and then I'd take all of this and divide it by the sum, again, where my index went from 1 up to the number of pieces that I had, okay, of just wi. Right? And the denominator of that little fraction right there really just gives me my total amount of weight. Right? That's all I'm doing there is summing up what's my total amount of weight. All right? And this equation right here is the basis of basically everything else that we're going to do today. All right? And we did it really just by doing a sum of moments around a point for this body. And it holds for however many little bits of weight that we want to have in our system. This is for a one-dimensional system. All right? Can we do it for a higher number of dimensions? Interesting question, okay? So let's take a look. What if I have a similar situation where I have some weights that are all now, instead of setting on a massless little beam, I have them set on this massless plate. And my goal this time is to try to figure out where should I screw in a little bit of a, like maybe say an eye hook into this plate, so that if I suspend it from above on a string, right, it would balance that plate. Okay? Same question, right? It's the same question. It's just now a two-dimensional question as opposed to a one-dimensional question. Now, what do you think the answer is going to be? Okay? You don't know. It's a mystery. All right? But if we were to guess, we would probably say something like this. There's probably going to be an x coordinate of this location. Right? And I'll call that x sub c. There's also going to be a y coordinate of this location, right? And maybe I'll call that y sub c. All right? And we could do the exact same thing we did before, and some moments around an axis, right, that goes through that eye hook, either aligned with the y direction or with the x direction. We could do it around two different axes. And at the end of the day, the little derivation, the little development thing that I just did a second ago would look exactly the same. And so I won't do it again because I think that would end up being boring. But I'll just go ahead and tell you that x sub c is all it's going to do is going to be equal to the sum, again, where my index values go from 1 up to however many pieces that I have in my system, right, of the weight of each piece times the x coordinate of each of those pieces. All of this divided by the sum for indexes that go from 1 up to the number of pieces that I have of just the weight of each of those pieces. Okay, that's for the x direction. That's basically the same thing we just found with the one-dimensional case. So with our two-dimensional case, the only thing that happens here is that we add a y sub c, and it has the same format basically, right? All we got to do is just say the sum for my index from 1 up to my total number of pieces of the weight of each piece times the y coordinate of each piece, all this divided by the sum over all of my pieces of the weight of each piece. Okay? And it's a little bit harder to describe in 3 dimensions, but what do you think happens if we move to 3 dimensions? You basically add another one of these equations that instead of having x's or y's, have z's wherever x's and y's show up in this equation. Okay? Now, the good news is in this class, we don't actually need to do a whole lot with, as a matter of fact, I don't think we do anything with 3-dimensional centers. All right? Even though such things can exist and maybe they are important in certain cases, it's not something that matters to us a whole lot in this class. Okay? Now, here's another question. We just did this for centers of gravity, all right? So this is all based on the idea that each one of these little elements has a force of gravity sort of pulling down on it, right? This one's going to be pulling down, down, you know. What's the difference between this and a center of mass?
This includes the force of gravity.
Okay? This is for forces. What we do with masses is basically the same idea. It's just harder to kind of describe what exactly are you summing moments around. I'll tell you this, as long as you are in a constant gravitational field, right, which we pretty much are, although you could make the argument that if I go a little bit higher, that my gravitational pull that's going to happen on things up there is going to be a little tiny bit less than if I'm lower, right? We're going to neglect that. Right? So we're just going to assume that in most of our cases that we're working on, if they're in a gravitational field at all, they're in a uniform gravitational field. And if so, then the center of mass is in the same place as the center of gravity. And one of the ways you can tell that is you can take each of these expressions here, so let me copy them and put them down here. All right, on the Earth at least, the relationship between weight and mass, what does that look like? Weight is equal to mass times gravity, right? So what if I go through these things and I divide by g? Right? Like I take this up here and I divide it by g and divide by g. Up here I divide by g and divide by g. What does this give me? Okay. X sub c is just going to be equal to, right, the sum for I equal 1 to n of m I xi, right, over the sum for I equal 1 to n of just mi. Okay? And similarly for y, right? Okay, so we can find a center of mass using the same type of an idea, right? And we can see there that because gravity is assumed to be constant, acceleration of gravity is assumed to be constant, we can just figure that out. Okay? Well, what if the pieces of material that we're talking about have a uniform density? Okay? What's the relationship between mass and volume? Okay, it's related by density, right? So we can basically say that mass is equal to what? Density, which rho is a lot of times a variable used for density, times volume. Okay, so what if I go through and I divide these expressions here by density? Put them over here. Okay, what changes? Instead of my masses, if I'm dividing by density, assuming density is a constant for everything in my system, what can I put there instead? Okay, V, right, where V is volume. Okay, so we basically go through and divide by rho, which is density, and it ends up giving me volume. All right? Now the next one is actually probably the one that matters the most to us, and maybe is the most difficult one for me to really describe. But imagine that we do this and then we have a piece of material that has a uniform thickness to it. Okay? And these are, you can imagine this as being a bunch of little, like almost little chunks of material, right? Like this is a whole bunch of just these little squares of material that compose this whole piece, right? They've got a uniform thickness, uniform density, right? What I would say is that the center of gravity of a plate like that is going to be based on the idea that there's a relationship between the thickness of this plate and the volume of each of my little elements of material, right? So if you think about this, imagine each one of these little elements has a particular cross-sectional area to it. I would say that we can figure out things like centers of volume. Oh, excuse me, not volume, I mean to say area. Centers of area. By sort of thinking of a case where we have uniform thickness, and in that case we're going to have that volume is going to be equal to that thickness times a cross-sectional area, or the kind of the frontal area of each one of those pieces. Okay? And so what does that do for us to figure out our center of area? Right? Going to be kind of the same thing again. Hopefully I've still got it in there. There it is. Okay. But now what do we replace the volume with? Okay. We're dividing through by thickness, right? We're taking this up here and dividing through by thickness. Oops. And we can get area. And this is actually a set of relationships that I'm going to be using a whole lot in this class, especially this last one. This, by the way, is how we come up with finding another name for this center of area, which is called a centroid. Okay? And when I have in the denominator of each of those the sum of all my little area pieces, what's another way of thinking of all the sum of all the little area pieces? It's really just the area of the whole top of a piece like this, right? It doesn't really matter what the shape is of the piece. It's the denominator is just the whole amount of area that I've got right there. Okay? Starting to look like a bit of kind of like a steak or something, making me hungry. Okay, so these are the relationships that we're going to start with here, and let's go ahead and do our first example problem to find what is the center of gravity of a rod made up of two different kinds of material. Okay, here's the two kinds of material, aluminum and steel, and it says find the center of gravity of this little two-segment rod, one segment being aluminum and the other one steel. Okay? So my first question is this. If we had to find the center of volume of this rod, would that be hard? How would you know what the center of volume would be of this rod? Okay, you have the diameter, you have the length. Basically, I'll mention this, it's because of symmetry, right? We mentioned before, anytime you have an axis or a point or a plane of symmetry, your centroid or your center, whatever center you're trying to find, is going to occur on that axis or point or plane of symmetry. And with respect to volume, we do have symmetry on this problem, right? It's just a plain rod, and so the point of, or the, I should say, plane of symmetry that happens horizontally for this rod is going to happen halfway along its length. So we've got 14 inches total. We would have 7 inches from one side would be the center of volume, right, as far as left and right. And then in terms of where throughout the cross-section of the rod the center of volume would be, where would that happen? Just right along the center axis, right? Because there's there's symmetry around an axis that goes through the middle of this rod. So we know exactly where that center of volume would be of this rod. But the center of gravity is a little bit harder for us to figure out because the density of this is not uniform. Okay, so we actually need to know the densities of aluminum and steel to answer this question. And where would we find those? All right, some of you may have seen these at some point, but the table that we use a lot that's in the back of the text, okay, which I'll try to find here momentarily. This table that has a lot of different kinds of materials, it's table A17 on page 704, has a few different densities listed for these aluminums. I'm going to say it looks like they're basically right around 0.1 pound per cubic inch, and it's given here as a specific weight, actually, not technically a density. Okay, so let's go ahead and put that in here. The specific weight of aluminum is 0.1 pound per cubic inch. Okay, and what about for steel? We can look through there. All right, most of the steels, until it gets into stainless steel, but most of the steels, it says 0.284. Same units, pounds per cubic inch. All right. Good so far. What do I need to do to figure out this center of gravity?
Find the weight of each segment.
Okay. I need to figure out, first of all, what's the center of each segment and how much weight acts at each segment. So like the steel segment right here is going to have a weight to it, and the aluminum segment here is going to have a weight to it. Because of the symmetry of the steel about itself and the asymmetry of the aluminum about itself, I know where each of those weights should act. The weight of the aluminum should act at the middle of the aluminum. The weight of the steel should act at the middle of the steel. Okay? So those are the things we need to find. Is first of all, how much do each of them weigh, and then what are those dimensions to each of those locations. Since I already talked about it, let's go ahead and write what these dimensions are. It's 5 inches to the weight of the aluminum. How far is it to the weight of the steel? Okay. It'll be 10 inches to one side, plus a little bit more, plus 2 inches to go to the middle of the steel, right? So that'll actually end up being 12 inches. So notice here I'm being pretty careful. When you do these dimensions to figure out where the centers are, and you're doing these centers calculations, you have to pick a point to measure all of your centers relative to, right? I'm picking the left end of this entire rod to measure the locations of my centers relative to. Okay? So now what's the weight of the aluminum?
Volume times the density.
Okay? It'll be equal to the volume times the density. So the volume is just going to be equal to pi times 1 inch over 4 times what? Okay. First of all, times 10 inches, right? I'm trying to figure out the total amount of volume of the aluminum. So I need the cross-sectional area of the aluminum times how far its length is. Then I need to multiply by the density of it. So multiply by 0.1 pound per cubic inch. Okay. So let's go ahead and do pi times 10 times 0.1. Oops, I missed something here. I guess it won't matter for this example, but what did I miss? That should be squared right there. Okay. Pi times 10 times 0.1 over 4. Which gives me 0.7854 units. Okay. My cubic inches are going to cancel all my inches there. It'll just be in pounds. What's the weight of the steel? Same idea, right? Difference being that the steel is 4 inches long and that the density of the steel is over double the density of the aluminum. Okay, so when I punch all of that in, I'll end up with pi times 4 times 0.284 divided by 4. Okay, 0.8922. Okay, well then what? All right, now I just apply my equation, right? The center right? My x sub c value, the center for what I'm trying to find, is just going to be equal to the sum, I equal 1 to n, in our case, I equal 1 to 2, right? And the sum, I equal 1 to 2, of what? wi xi over wi. This is, that's what our equation says, right? So what do we plug in for these? Okay. We'll use aluminum as the first piece. And by the way, that's a lot of times handy to go ahead and number. I'm going to do my aluminum first, so I'll use kind of an index of 1 for all my aluminum questions and an index of 2 for all my steel questions, right? And that's basically what would go into the little I values if you were thinking of the summation notation. Well, we'll just go ahead and sub in these values, right? So for the aluminum, we'll say 0.7854 pounds times 5 inches plus 0.8922 pounds times 12 inches. And all this gets divided by 0.7854 pounds plus 0.8922 pounds. Okay? And that's just the total amount of weight of the rod. So let's plug these in. .7854 times 5 plus 0.8922 times 12 over 0.7854 plus 0.8922. 8.723. Okay? I'm sorry. Not, did I put pounds, right? Is that right? Good job. What should I put there instead? Okay, you'll notice the pounds cancel the pounds on this, so it should not be pounds, it should be inches. Okay? And so basically what we have figured out with this problem is that if I want to know, like let's say I'm having to support a member like this across 2 supports and I'm trying to just support its self-weight. What I can do here is I can say that the overall weight of a member like this, which is going to be what? This value right here. Actually, let's calculate that all by itself real quick. What is 0.7854 plus 0.8922? Okay. 1.6776. I basically say that if I take a weight of that 1.6, what was it? 776 pounds, and I put it at a distance of 8.723 inches away from the same axis that I did my original measurements with respect to, then that would cause the same reactions on the piece that's holding it up, right? I don't have to look at individually the reactions of each one. I basically found where the weight of the overall piece should be centered so that it causes the same kind of reactions at the supports. Does that make sense? Okay. Nice little warm-up. Shall we make it a little more tricky? Okay. Here's why it gets a little bit trickier. We can have shapes that don't have nice little discrete pieces. All right? So here's an example of a shape that doesn't have a nice, like, it's not little square pieces, right? It's got a curvy edge on it. Okay? And let's do this. Let's actually figure out what the center of area is of this shape, but we won't even give you a specific r value. Let's do this in terms of any r, right? Any radius value of this little quarter circle. Okay? So if this is, I'll go ahead and tell you that, it's a quarter circle. You tell me, what is the equation for the curve that makes a quarter circle? Okay? I hear someone saying it's based on this idea that x squared plus y squared is equal to what? R squared? Okay? We do it with polar coordinates. Let's just do it with rectangular coordinates. So let's actually solve this thing and say y squared is equal to r squared minus x squared, which means y is equal to the square root of r squared minus x squared. Technically, what should it really be? Plus or minus, but what is it for us? If this is, okay? Yeah, so this will be just the positive side because we just really need the part that's above the axis there, right? Okay. Good so far. That's the equation of the curve. How do I figure out what the centroid is of this shape? Well, you didn't think you were going to do calculus in here today, did you? All right. Here it comes anyway. Let me tell you this. The most important thing about you having learned calculus is not you knowing how to do integrals. You know, pieces of software know how to do integrals. What's the most important thing about you learning calculus? Okay? Knowing how to apply it, and knowing how to apply it is really mostly about figuring out how to come up with your infinitesimally small element, whatever that is. Right? Because all of calculus is about, you know, coming up with some infinitesimally small piece and either summing up a bunch of those, right, or finding a difference in one direction and a difference in the other direction and figuring out a slope, right? That's basically all of calculus. You're doing that kind of stuff. So for this, how do we come up with a little element that is useful with what we just learned to figure out what the centroid is of this area? Let me show you. What we're going to do here is we're going to imagine this being a series of little rectangles. How did you guess? Okay. And where is the center of that little rectangle? Okay. Right in the middle of that little rectangle. Okay. So what is the x coordinate of that little center of that rectangle? And what is it just kind of generally? It is just the x coordinate based on how I centered this thing. So just whatever my x value is at that location, that is the x location of the middle of that rectangle. Okay? Now I could make the width of this, you know, something finite in size, let's say a delta x, right? But then I would, you know, I'd have a finite number of them and we could do all of that. But even more handy is what if we make this narrower, right, than a finite size and say, let's say this is a tiny little width of dx. Okay? Good place to start. Now let's think about our formula, right? We're saying that x sub c is going to be equal to the sum of I equal 1 to n of what? A I x I over sum I equal 1 to n of ai. Now, how many terms do I have now that I made that thing infinitesimally small? I've got an infinite amount of terms, right? So how does this change, you think? Okay. You do a limit as the number of terms goes to infinity, right? And as the width of each one goes to 0. Crazy. What does that become? An integral, right? Of what? Okay. I'll say it this way. Our x coordinate is still what we're going to use there, but we need to then multiply by a little differential amount of area, an infinitesimally small amount of area, and divide all of that by, or not divide, integrate it over the total amount of area. Okay? And what do we do in the denominator? Okay? This is more the integral form, the kind of the continuously variable form of the same equation that I just did a second ago. So for our problem, what we want to do is x sub c is going to be equal to an integral. Someone said, let's go from 0 to r, right? The reason that we know we want to go from 0 to r is we're going to let our x coordinate vary from our leftmost rectangle, which is 0, over to our rightmost rectangle, which is going to be at r. Okay? And x, we just pull that over, right? We already said the x coordinate of this little rectangle is just x. But the tricky part is, what is dA? Okay? dx times the height of this thing, right? So actually, the dA is going to be equal to dx times y of x. Right? And what's y of x? Right? So we go up here and say this is just multiplied by the square root of r squared minus x squared dx. And what do I put in the denominator? Yeah. Thank you. Someone said, is that supposed to be y of x times dx instead of dA? And that is absolutely true. Thank you. All right. So what do I put in the denominator? All right. Like I said a second ago, actually doing integrals isn't the main part, right? I believe that you guys could do this if you really had to. What do you think this becomes? Okay. Okay. You want to know how I know that? I've done it a few times, but if you didn't know that because you've done it a few times, right, you can go to a table like this one. Okay. This is one of the tables that's in your textbook. And you might notice that the entry right here for the quadrant of a circle, you'll see there that the x coordinate, right, is this 4r over 3 pi. Okay? But that's what comes out of doing a little integral calculation like this one. Yeah?
So that would be
Right. So his question is, would that be in the reference material on the test? And the answer is yes, it is. This is one of the pages that's in the reference manual that's in your book. Right? So that's nice. You'll know what these are for some common shapes. Some of you might be looking at this and saying, there it has a quarter circular arc, and then it also has a quadrant of a circle. What's the difference? Okay. I'll tell you what the difference is. What we just found was the centroid of an area, right? And it was an area bounded according to a quarter circle, right? Bounded by that quarter circular shape. Over there on the left is a quarter circular arc. You can kind of imagine that being a wire that's bent into the shape of a quarter circle. And there's occasions where we need to know what the centroid is of a shape like that. Okay?
Why isn't our centroid on the line then?
Why isn't the centroid on the line?
For the quarter circle arc.
On what line?
Like, why isn't it on the thin wire line?
Okay. His question is, why isn't the centroid on the thin wire line? Should it be? No, it shouldn't be, right? Because by it being curved, it's going to shift the center of gravity. You can imagine it actually having some mass. It's going to shift the center of gravity to some location that's not actually on itself, right? And you can figure out where that center of gravity would be located based on those equations right there. Okay? So this is actually a really good point. I've seen a lot of students, whenever they get onto the exam and they have this reference material with them, and they're supposed to find, let's say they're doing a semicircle, right? And they're trying to figure out where the centroid is of a semicircle, and they use that picture that's there on the left instead of the picture that's on the right. Easy to do, but make sure you know what the difference is and which one you should be using, right? For when doing areas, you want to use the ones that are shaded. All right. Let me show you one other thing with respect to finding these centroids of these areas. What if I wanted to figure out my Y centroid? Okay. Now, this is actually, we can use the exact same picture with the exact same logic. The only difference is that the original equation, if we were looking in the Y, would be that it would be the integral over the area of y dA over the integral over the area of dA. And so when we get ready to actually populate this equation with our real things, if we've split this up according to little differential elements in the x, in other words, where our little infinitesimally small size is in the x direction, then we probably want to make all of our variables expressed with respect to x instead of y, right? So we don't want to just leave a y in there. Well, how would we convert from y to x, like change this y into something in terms of x? Okay. You basically solve it. You can still go from 0 to r, but you solve it and you say, what is this height, right, of this location in the middle? That is what we're referring to with this y value right here. It's what is the center of each of my little rectangles, and what is the height of that? Right? It's going to be the square root of r squared minus x squared over 2. Okay? Because we want the center of each one of our little elements. Right? And so when we plug that in, it ends up being square root of r squared minus x squared over 2 times our dA, which is going to be the square root of r squared minus x squared dx. All of this over the integral from 0 to r of just r squared minus x squared, square root of that, dx. Okay, so you'll notice there, it's almost exactly the same as what I did for x. The only difference is I plugged in for y an expression that gives me the centroid of each of those rectangles in terms of x. Okay? And if I solve this out, what do you think you'll end up finding? Okay, and how could you know that without solving anything actually? Remember, your centroid is always on an axis, plane, or point of symmetry if one exists, right? So think about this here. There is an axis of symmetry for this diagram at 45 degrees. So once I figure out that it's 4r over 3 pi in the horizontal direction, right? That must mean it's also 4 over 3 pi in the vertical direction. Okay? So you knew that already. And let me actually do one thing better for you here. We can do this sort of once and for all mentally and say, if you want to just split this up in one direction, like let's say you only want to split it up in the x, you can do this so that you find your y sub c with this. You can say this is really just going to be equal to the integral over the area, right, of f of x over 2, right, dA. Right? In other words, it works no matter what the function is. You're always going to be taking half of the height to get the centroid of each of those rectangles. Right? And I should have put, what should I have put there? F of x squared. And then here I should have put what? Okay? In other words, no matter what function that you put in there, you can just square that function and divide it by 2 and use dx, and you'll be able to figure out what the y-coordinate is of the centroid without having to split it up again along the other axis. Okay? All right, so that is an example of finding something by integration. And I showed you a second ago, there's probably an easier way because a lot of shapes are common shapes. And you don't imagine that people necessarily go in and reintegrate each time that you see another common shape out there of something that you need to know, right? And so, if you come up with some sort of a complicated shape that might be a construction of a number of other shapes, we want to be able to find the centroid of those kinds of things without having to integrate. Right? So how do we do that? Well, I'm glad you asked. What if I want to figure out the centroid of a shape like this where it's a quarter circle with a triangle cut out of the middle of it? And that composite shape, right, that's what we call that. Composite shape is basically a shape made up of adding and subtracting other common shapes. Right? How do I figure out where the centroid is of a shape like this? Okay? This shape can be thought of as being a quarter circle, something like this, minus a triangle. Okay? We can literally sort of add and subtract little areas like this and figure out an overall centroid. Okay? And what we're going to do is we're going to have to figure out what the areas are of each of the pieces and the locations of the centroids of each of the pieces. And we can again apply the same kind of an equation as we did before. The sum of each of the areas times their x-coordinate over the sum of all the areas. Right? That'll give us our x-coordinate of the centroid of the shape, and we can do the same thing in the y. And one of the ways that I think this is, it gets a little bit easier is to think of doing this in a tabular kind of a format. Right? And here's what I mean by that. Okay? I'm going to define two different regions. I'm going to put them in this table. So let's say my region 1 is the quarter circle, and my region 2 is the triangle here. Okay? So I'm going to go ahead and define those in my table and say I'm going to make a row in my table for region 1 and a row in my table for region 2. Okay? My next entry in the table, I'm going to figure out what the areas are of each of those regions. All right? What's the area of region 1? Or how do I figure out the area? All right? I'd say it looks like the quarter circle here is going to have a 2-inch radius, right? Whether I read that along the bottom, it'd be 1 inch plus 3/4 plus 1/4, right? That'd be 2 inches. Up here I have 0.75 plus 0.75 gives me 1.5 inches, plus 1/2 inch gives me 2 inches. So what we're saying here is that the total area of the overall circle would be pi times 2 inches squared, right? And then that we will divide by 4 because it's a quarter circle. All right, so let's go ahead and punch this in. Pi times 2 inches squared over 4. Right? Thank you, Casio. Okay, I'll tell you what, I'm going to put that down here, if it lets me. Please, tablet, may I put this down here? Thank you. All right. Good enough. Now what's the area of the next piece? Okay. So for the next piece, it's going to be equal to 1/2 base times height. So 1/2 of the base is 1 inch. The height is 0.75 inches. Okay. So what does this become? 0.5 times 1 times 0.75, 0.375. Now, that's what the area is. But how should I count it? Okay, think of it this way. Region 1, I counted area that's not really there. Why? Because this triangle's missing out of it. So in order to get the right area, I don't count this area as a positive area. I count this area as a negative area, because I'm having to remove area that I already counted on my last step in order to get the right amount of area, right? So I'm going to count this as a negative area. Okay? I'll leave that alone for right now. What I want to do for the next stage is go ahead and identify what are the x coordinates. I'm going to label this here with x sub I. But what are the x coordinates of the centroids of each of these areas? Okay, we just learned what it would be for the quarter circle, right? The formula for it would be 4 times r. R is 2 inches over 3 pi. Right? So this would be what? 4 times 2 over 3 pi. Point 8488. Units, inches. Excuse me. Okay, so there's that. And then for region 2, what is my x coordinate of the centroid of region 2? Which, by the way, actually, I should make this very, very clear. When I did this 0.8488, what was I using as my reference location? All right? I used over here, and I said I found where is this going to be relative to this edge. When I do it for region 2, where should be my reference location? I should use actually the same reference location. When I say where is my x sub I position, right, it's going to be somewhere in this triangle, right? But I need to measure it again relative to the same edge. Okay? So whatever I come up with here is going to have to be 0.25 inches plus whatever that extra little bit's going to be to get to the center of the triangle. Okay? And I don't expect you to know that yet, but we can look at this sheet that we have right here. And one of the things that we have is a triangular area. And we have to be very careful with this triangular area, because this is another mistake I see get made a lot on homework or whatever. Whenever you're trying to find the centroid of a triangle, a lot of times people will blindly just look at the equations here and they say, okay, so the x direction, all I need is just 2 times b over 3, right? And they see the b is the width, and so if that, you know, for the problem we're solving here, if it's 1 inch wide for that little triangle right there, you know, that's easy enough. It'll just go 2/3 of the way across that, so it'll be 2.25 inches plus 2/3 of 1 inch. What's wrong with that thinking? What direction is this triangle relative to the one in the reference material? Okay? They're opposite each other. And so what the reference material is saying is when you're in a right triangle like this, you find the centroid by going 2/3 of the way from a point of the triangle to a flat of the triangle. That would be the same thing as saying 1/3 of the way from a flat of the triangle to the point. If you're measuring starting on this side, you're only going to go 1/3 of the way to the point to get to the centroid. Right? And that's more like what we have in our case. So what we're going to do is go 0.25 inches plus 1 inch over 3. Okay? So 0.25 plus 1 over 3. 0.5833 inches. Okay. Now let me show you what we're going to do with the next step here. What we're doing is we're trying to set ourselves up to be able to easily do this equation to find the x sub c, where we're summing up a sub I, x sub I, and then in the denominator we're just summing up a sub I. Like this. So what that sum of a sub I, x sub I basically is we're going to take products of this and this and products of this and this. We can actually make another column for this. I'm going to call it a sub I, x sub I. Right? And we can go ahead and multiply these values together. Okay, 3.1416 times 0.8488 gives me 2.667. And what do I have for my next one? Negative 0.375 times 0.5833 gives me negative, what was it? 0.2187. And up here, what should I have put for my units? These units aren't right. Okay, inches cubed is what that comes out to be. And why do you think it might be good for me to come up with those products, those two products? So what I can do now is I can take those two products that I did right there and add them up. So I can add to negative 0.2187, 2.667. That'll give me 2.448 inches cubed, right? If I do that same thing over here for the area and take 3.1416 and subtract 0.375, that gives me my total amount of area. So down here I'll have 2.7667, or just 767, I'll do that way. Okay, this would be in square inches. So how do you think I come up with my x sub c value? .448 inches cubed over 2.767 inches squared, right? And that will give me my x location of the centroid of this composite shape. So 0.448 divided by, I think that was my previous answer, so I'll just do that. 0.885 inches. So what that tells me is that if I'm trying to figure out my overall centroid of this shape, I've got to measure over by 0.885 inches, wherever that is, and my x direction or x location of my centroid is going to be that far from the same axis I did my previous measurements relative to. Okay? That's a really important thing. You have to define your axis you're making all your measurements relative to, because then once you find a dimension that gives you the location of your centroid, you're going to measure that with respect to the same axis you started off with. Okay? So it's really important to make sure you know which axis that is and stay consistent with it. All right? What if I want my y direction? Okay? Basically the same type of process. All I got to do really is just add another couple of columns, right? My y sub I column. How do I figure out where my y sub I values are? Okay? For region 1, again, it's just going to be equal to 4r over 3 pi. So 4 times 2 inches over 3 pi. And so that just ends up giving me the same number, right? What was it? 0.8488 inches. What about my, for the triangle? Okay, 0.5 inches plus 1/3 of the way from a flat to a point. This is 3/4 of an inch high, right? So 1/3 of the way from the flat to the point is going to be 1/4. Okay, and once I've got all that, I can figure out a sub I, y sub I, right? Just by multiplying the area I had over here on this far left column, which actually ends up being the same thing, right, for this first entry. It'll still be 2.667 inches cubed. But what about for the next one? Okay, next one I'll have negative 0.375 times 0.75. right? And this will give me negative 0.2813, we'll say. Inches cubed. Now what? Okay. We'll add what I just came up with there to 2.667. This gives me 2.386. Inches cubed. And how do I come up with my y direction centroid location? 2.386 inches cubed over 2.767 inches squared. Right, and that gives me 0.862 inches. Right, and so where do I measure that? Okay. Yeah, I started all of my measurements for that second phase where I was doing my y directions. I was doing all of my measurements relative to this axis down here, right? So that means that when I measure up to find my centroid, right, it's going to be 0.862. I measure up here, and wherever these two things intersect with each other, that is my centroid of the overall shape, right? And this height, I guess I'll just write it over here, 0.862 inches. Okay? So, I want to make sure you're super clear on these reference axes, right? Make sure that when you're doing these things, you establish the location. You're doing all of your measurements for each of your x locations of the centers of each of the component shapes, right? Measure all of those relative to the same axis in one direction, and in the y direction do the same thing. Measure them all relative to the same zero axis. And then once you come up with numbers, those are numbers that give you location of the centroid relative to those same axes used as your zero axes in the starting of the process. Okay. Now, any questions? We have, yeah?
If it's not explicitly stated, how do you assume, or how do you find out, like, what somebody else's reference angles were?
His question is, if it's not explicitly stated, how do you figure out what someone else's axes were? And the answer to that is you can't really unless you try to back calculate and figure out where they must have been, right? So if someone, let's say it's a problem where you've been tasked with finding the centroid location, and you're supposed to enter a number, then whoever asked you to do that needs to give you what they want you to enter that number with respect to, right? And whoever's asking you the question will then have to tell you where that location is, and that gives you a hint as to what location you should use as your reference, right? Because it is all relative. Like, I could have done this same exact problem, and instead of essentially establishing an axis here, which is what I did, and an axis here, basically that's what I did is I said, those are my reference axes, and I'm making all my measurements relative to those. There's nothing that would have stopped me, per se, from choosing something different. I could have chosen a y-axis here, right? What would have happened? I would have had to measure to the centroid of the triangle relative to that axis, and I would have had to measure to the centroid of the quarter circle relative to this axis. I would have had to work all my math out. I would have come up with a negative number at the end of it. And then what would that mean? It means I'm going to take that same measurement relative to this axis and figure out where the centroid is of the whole shape based on that. So Anyway, my point is the axes are arbitrary that you pick, but the actual centroidal location that you come up with will be the same regardless of what you chose as your reference axes. Okay? I know this is a little bit tricky when you do online homework and they're just trying to get you to enter a number. When you do that, you have to enter that number with respect to whatever axis the homework told you was the reference axis.
That's why I asked.
Yeah. Yeah.
Is the chart a good way to make sure you don't get lost in calculations? Is that, because I could see myself like midway through the problem.
I think what you're saying is doing this tabular solution like this, is this a good way to try to keep yourself from getting lost partway through the solution? The answer is 100%. Because there's nothing hard about any one of the bits of math that you have to do with this. It's the fact you have to stack it all up, right? And so having some way of organizing your thoughts, even though my stuff here wound up looking a little messy, you know, yours could probably end up, I'm trying to show you the source of the calculation and the result of the calculation all there in the same cell. That's why it looks a little bit messy. But when you start working on it, you can make it look a lot neater than this. The other thing you can do is do it in a spreadsheet. There's nothing wrong with doing something like this in a spreadsheet because that makes it simpler, especially if you have a large number of areas. Okay? Yeah? Was there another?
No, I was just thinking about the spreadsheet idea because then you can just make variables and start plugging things in.
Spreadsheet is a great idea, right? It makes it easy. With one little warning, right? If you learn how to do things with software and then that software is unavailable to you when you have to perform on an assessment, like an exam, that can end up biting you in the rear a little bit. So just be careful with that to make sure you're not leaning on it too heavily. Make sure you also know how to do it another way. But yeah, the table is a really good way of keeping your thoughts straight about each of these areas that you're going to have. All right, one other example. We excited? All right, we talked about distributed loads, I think, last time. Okay? And whenever we're trying to figure out distributed loads, the thing you need to know is that this basically is another application for the question of centroids, right? Once you know that the distributed load is shaped a certain way, you know, in other words, it's graphed out in a way where the height is proportional to the amount of distributed load, right? And the width is just the physical width, then if we can figure out where the centroid is of that area, that gives us the position where we should apply a lumped load, right? This is another word for saying this is we're lumping the load at a particular location. We know where to lump the load based on where the centroid is at. Okay? So here's our problem. The height of it at the horizontal part right there is 20 pounds per foot, and the widths are given on the figure. How do we figure out where we should lump the lumped equivalent load that would cause the same reaction at the two supports? Okay? What do you think the first step might be here? All right. Let's name some regions. Let's say that we've got basically cutting off right here, right? We've got a rectangular region over here that we will number 1 and a triangular region over here that we will number 2. Okay? So let's name those over here and say region 1 and 2. And in the next column, you might say area. I'm going to put that in quotes. Because when we find the area, it's not really an area, is it? It's an area on this chart, on this graph, right? But it's the area is not going to have units of, say, length to the second power. Okay? So let's see, what would that area look like for region number 1? Okay, 20 pounds per foot times 8 feet. Okay, so what is our area? Yeah, it's going to end up in units of pounds because you'll see there the feet will cancel. And what's 20 times 8? Okay. 160? Okay. 160 pounds. What about for region 2? Okay, again, 1/2 times the base. The base is 6 feet. Times the height, which is again 20 pounds per foot. And so the area we come up with there will end up basically being 3 feet times 20 pounds per foot. And what will that be? 60? 60 pounds. When I sum this up, what do I get? Right? It ends up being, 220 pounds. But what is that? That's the total amount of distributed load that's on the beam. Okay? That's what that value means. Now what do I do in my next step? Okay. Let's go ahead and establish our coordinates, right? Let's say this is my x direction, and I'll call this my y direction, meaning this is my 0 location over here on the left. Okay. So my x sub I values, what is it going to be for region 1? 4 feet. The reason you know that is you're going to go halfway across that rectangular region right there. So we'll say 4 feet. Okay. For region 2. Okay. Right. So locally in the triangle, it's 1/3 of the way from a flat to a point. Right? So for 6 feet, that would be 2 feet from the flat to the centroid within the triangle. But what we got to remember is we're not going just to that point. We need to go all the way from our 0 location over to that point. So that'll be 8 feet plus 2 feet. So that'll be 10 feet. And that's what I'll put here. Okay. Now over here, when I multiply these together, I'll have 4 feet times 160 pounds. Okay, 640. Okay, what would my units be there? Foot-pounds. And in the next one, I'll take 10 feet times 60 pounds, which will be 600 foot-pounds. When I add these up, I'll end up with 1240 foot-pounds. Okay. And when I come up with a centroid for this, it's based on 1,240 foot-pounds over 220 pounds. Which is just going to be equal to 5.6363, right? I'll say 5.64. Okay, units ends up being in feet. Okay, and where do I measure that relative to? Okay, Yeah, so over here, this is the axis where I measured all of my zeros. And so if I measure over 5.64 feet, okay, kind of running out of space here, but let me just do it right here. 5.64 feet. And let's say that ends up being a location right in here. What does it mean I can do then? I can replace all of this distributed load with one concentrated load. Let's say something like this. That has a value of 220 pounds and is located at 5.64 feet to the center relative to that same edge. And that concentrated force that I put right there will have the same effect as far as the reactions at the supports as my actual distributed load that we had to begin with. Okay? And so this is a handy way for us to come up with how to lump a distributed load into a concentrated load that has the same effect for the support reactions. Okay? One other comment, because I haven't talked that much about what causes distributed loads, right? So there's a few things out there that you could think of that cause distributed load. Probably the most obvious one is self-weight, right? If you have self-weight of an object, especially if it's got a uniform cross-sectional area to it and uniform density and everything along its length, how would you model the self-weight of that body really correctly? Just a uniform distributed load, one value across the whole thing. If it's got uniform cross-sectional area, uniform density, right, it'll just be a uniform distributed load across the entire length of the piece. Okay? So that's the most obvious one. Another thing that may not be as obvious is, what if you have a pile of some kind of stuff on top of a beam, right? Let's say you've got a pile of sand or a pile of dirt or whatever you might think, grain, you know, and you have that pile such that, you know, the height of the material that's stacked up, right, what is that going to be proportional to? Kind of the local weight at that location, right? So like what if I, you know, what if I gave you an interesting question where you have a beam and I have like a retaining wall on this end, and I pile up some grain, and the grain makes a, you know, maybe it settles into more or less a parabolic shape. But one end is like chopped off, right, because it's got this little retaining wall that's holding it up. And let's say I've got some supports, you know, here and here. And what I'm telling you is I'll give you a function that tells you how high this grain is as a function of where you are located along an x direction, for instance. What can you do with that height? Okay? If you know the density of the material that's being stacked, right, then what you can essentially imagine doing is slicing this up into these little columns that are based on the height. From that column, you can figure out a little volume of that column. And if you know the density of the thing being stacked, then what does that give you for that little column? Mass or weight, depending on whether you're talking about a true density versus a specific weight, right? And then, so that means that little column, you have a weight, you can, you know, integrate that over the entire length and figure out what the centroid is of that area, and you can end up finding a location where you should lump all of that load to get the same reactions at the supports, right? So I'm not doing this problem right now, but I'm getting you to think conceptually of, you know, this is a place where this kind of thing could arise if you have the height of a stack of something that's variable over the length of a support. You might need to find what the centroid is of that pile so that you can figure out where to apply a lumped load and get the reactions at the supports. Okay? Does that scare you? Not trying to scare you, but you know, I want you to have an idea that there are applications where this might matter. All right. Well, I will let you go. Thank you for your attention.